for constraint systems, as I told you, canonical Hamiltonian has only actually a formal meaning, but that's it. Otherwise you cannot really even define it due to inconsistency, because you cannot invert all the momenta or the coordinates, and some of the coordinates just remain as coordinates. You cannot invert them in terms of momenta. So this is a problem, and to avoid this, we follow the Dirac prescription or the Dirac analysis. And this is that you define what's called a total Hamiltonian. This is the formal canonical Hamiltonian for getting constraints and whatever you have, just a formula of efficiency. And you add to this lambda A phi A. So phi A are the primary constraints of the theory, and these are the Lagrange multipliers which enforce these constraints. So by primary constraints, we mean constraints which directly follow from the Lagrangian by the definition of the momenta. So those momenta which are not expressed in terms of the velocities, those are called constraints. And they will appear in the definition of the total Hamiltonian in the following way. So the time evolution, that is if you take some operator, you want to compute its time evolution, you have to take its bracket, not with the canonical Hamiltonian, but you have to take its bracket with the total. So any variable, say A dot, if I want to take, then I will have to take its bracket. Also, we introduced the notion of the weak and the strong equality. So, constraints are all weakly imposed. So, if you have these constraints, this is a weak equality, which means that whenever you are going to compute an algebra, then you cannot set this to 0 inside the algebra. So, suppose I have to compute this with say A, with phi A, then this is of course not equal to 0, because naively one would expect that if this is 0, if this is the constraint, it's phi A is equal to 0, I would put 0 here. No, you cannot do that. So suppose the constraint is like, say, just P is weakly 0, so this will be the momentum P, then you have to take the algebra of A with P and you get some result. But once you have computed the algebra, then on the right hand side you can always put this to 0. So this is a weak equality. Only this matters. All changes are only proportional to the linear term of the constraint, because if you have a square of the constraint, that's always 0. That also I told you. So any algebra, say if you have A with phi A square, say, this you can always write because of algebra as phi A with A, and then another term, so this will be something like twice. But you see, this is outside the algebra, so here you can put this equal to 0, so this is equal to 0. Thus you can see that although phi A, even if this is weakly 0, its square of the constraint is always 0, strongly 0, and of course the cube will form power of 0. So, after this, we introduced the notion of what's called the primary and the secondary constraint, which means that to have a consistent evolution, the constraint should actually be time preserved. I mean, it means that if you have a constraint at some instant of time, say at the beginning, then that constraint must be preserved, which means that this should be valid at all times, which means that its time evolution 0. So if I take the phi a dot, so phi a dot, and that I'm taking the bracket with the total components, and that has to be, everything has to be 0. And from this we have three possibilities, as I told you. It could be something which is trivial. That is, if you compute the left hand side, you get 0. So 0 is with the 0, you get no new information. It could so happen that this gives me some finite object which involves these lambdas. You can see that the lambda will now come because lambda is a part of HD. And then it could also happen that if you have invertible algebra and so on, you can actually fix your lambda. So if the situation is such that you can fix the lambda, then you say that this is the second class constraint. If you cannot fix the lambda, then of course what will happen, the left hand side will have peso. ক্লাস নিচ্ছি আমি পরে কথা বলবো ক্লাস নিচ্ছি আমি পরে কথা বলবো Okay. So as I was telling you that the final case of course is that you will have something which will be which will not where you cannot fix the lambda. That has to be equal to 0. So that's a new constraint in the system. So these constraints are called the secondary constraints. And again, you have to, this is called an iterative process. You have to continue the iterative process. That is, you have to check the time consistency of the secondary constraint also. And you have to go down unless and until you come to the point when you have 0 is equal to 0, the process terminates. So the process will terminate, and then you have a whole set of constraints, and now you have everything under your control. You have the primary constraints, you have the new set of constraints which are called the secondary set of constraints. So this is one classification of constraints. This is called the classification of primary and secondary constraints. In the secondary set, I include everything. That is, constraints which follow from secondary, which we call tertiary, quaternary, and so on. But all these constraints in one whole, we will term them as secondary and primary. It's the basic set of constraints. So this is one classification of constraints. The other classification of constraints is, as I told you, the first class and the second class. The second class are those constraints where you can fix the lambda, and as you can clearly see from yourself that will happen when the constraint matrix has an inverse. So, for instance, in the left hand side, and you can check for yourself that if you can write phi k with hc, this is the first term. Then you have lambda b, and just change the index. This is the second. The algebra of phi with lambda is immaterial because the phi k is sitting outside, so that goes to 0. And this equal to 0. So now you can see that if this is an invertible matrix. You can write this in a matricial form. You can invert this, then of course you can fix that. you cannot infer this, then you cannot fix that. So, you can actually easily see for yourself that this, if this has a form like this, if it has a form like this, yes, you can obviously see that you will not be able to fix lambda because this is zero. So you will not be able, in other words, you will not be able to invert this. This is therefore called the first class sector, which is defined like this. So constraints which satisfy this property are called first class constraints. If they do not satisfy this property, the second class, as simple as that. Then you will be able to fix them. So this is the other classification of constraints. This is called usually FCC or SCC. First class constraints or second class constraints. So we have two basic classifications of the constraints. Right. Now, the one thing that should be observed in this entire analysis is that it's strictly a semi-classical analysis, that is not quantitative stuff, because you are always working with what? Poisson brackets. It is not completely classical because of this funny behavior, because you distinguish between what's called the weak equality and strong equality, therefore then this approach is called a semi-classical approach. You can, of course, proceed with the quantization, then the quantization program as you do, that you have to replace the brackets by the I times the commutators, and so on and so forth. But that's a more complicated picture. Before going to the quantum theory, even in the semi-classical picture, there are many decent points which should be emphasized. The first point is that these files basically act as what's called the generator of the gauge transformations. They define really the physical Hilbert space. The subspace, which is really the physical Hilbert space, is defined by these files in the following way. So here, if I take this phi as just f, I mean by phi is a first class constraint, and then this annihilates the physical states. Okay, so this is how Dirac defines the physical states. So you have a complete Hilbert space for a first-class theory. All gauge theories, gravitational theories, basically all first-class theories. So you know that you have redundant degrees of freedom and so on and so forth. In this Hamiltonian picture, you can abstract the physical or the subset of the entire Hilbert space, the physical space, by this definition, by this first-class constraint acting on this psi annihilates. Now, you can actually check the validity of this in similar ways. For instance, if when you will work with a quantum theory, then you can actually replace this relation which I have written by an I, and the Poisson bracket by an appropriate commutator. You can now see that if you add psi p on both sides of this equation, it's a valid equation. If you add psi p here, and add psi p here. So you see the right hand side is 0, but the left hand side is also 0, because this as a commutator is phi a phi b minus phi b phi a. But whether it is phi b or phi a or first class, it's acting on side that's 0, so 0. So this is a valid definition. This is a valid definition. and it is valid only if this is first class. If this is second class, this is not valid. That's very easy to check, because if this is a second class, this will be something like this. There is no phi on this side. Therefore, you can see, if you try to play this game here in the second class, and you apply a psi here and you apply a psi there, then you can see the left hand side is 0. If you use the same definition, but the right hand side is not 0. Therefore, there is a clash. And therefore, this really shows that for a second class system, this does work. I mean, only if you have a system that has only first class constraints, then you can isolate your physical input space by a definition which I have given in this. How to discuss with this deal with the second class is a different story, which I will come. Now, if this is the thing, you can see that if you interpret this as the generator of a gauge transformation, then you know that the finite transformation, which is built up by a succession of the infinitesimal transformations, when exponentiate this, then you write an I, and then you have the parameter, and then this is the generator. And that's showing that how this acts as the generator of the gauge transformation. This is all the first class constraint, right? And then these will act on psi p. Okay. So what is the first term? And that's all. When you expand the exponential, this will hit and this will give me 0. Right? So this is indeed the generator of the gauge transformation, because the physical states should be invariant. What are the physical states? The physical states are those states which are gauge invariant or invariant under the gauge transformation. They should not change. And therefore the generator acting on that should not change the physical state. And that's what happens. And this is once again compatible with the Dirac prescription that you define the physical state in that way. So this just shows how you interpret the first class constant. Now, what about the second class constant? The interpretation of second class constant is very tricky. Indeed, if there are second class constraints in the theory, there are two ways of discussing the problem. The first way is due to Dirac himself, where he says that you can redefine the Bose bracket, by introducing a completely new bracket, which is named after him and is called the Dirac bracket, such that if you use that bracket, the second class constants are all strongly 0. And if they are strongly 0, you can completely forget about them. Right? If they are strongly 0, there is no need to remember them. They are strongly 0. They are out. They are completely out of the dynamics. They are 0. How then to define the Dirac bracket such that the second class constraints can be interpreted to be strongly 0? I will show. So let us consider this phi b, say, this is a completely second class set. This is a second class set of constraints, no first class here. Then the Dirac bracket between any two variables, say PA these are not coordinates of momenta, they are completely general. So this is the Dirac bracket, and I denote this with an asterisk mark to distinguish it from a Poisson bracket, which will not have this asterisk mark. This, by definition, is the first term is the Poisson bracket itself. And then the second term these are the constraints. All brackets appearing on the right hand side are Poisson brackets. The bracket appearing on the left hand side is the Dirac bracket. The Dirac bracket is defined in the following way in terms of the Poisson bracket, where this is the inverse of the Poisson algebra of the second class constraints. So, lambda CD is this. This is the algebra of the second class constraints. The index down, the index taken up means this is the inverse of this. That's clear. This is the definition. Okay. Now you can see for yourself. I will come to the intricacies of this definition subsequently, but there is no water, as usual. This room has no water. Let me take the Dirac bracket of an arbitrary variable with the second class constraint. Right? So you can do this in this is PA, and instead of QB, let me take this to be phi B. So but this I have not written here in some indexes D. That should be understandable. So sometimes I may even forget the some notation, but that is implied always. Now QB is phi B. I have written that. So this is okay. So this part you can see is lambda CD, and this is what? This is the inverse of this. So what's that? That's delta C. This is the delta CB, and therefore you can see I can omit everything. Right. Delta CB. And then we want the contraction C just gives me what phi B. And then you see the power of Dirac's definition. Okay. So the Dirac bracket of any second class constraint with any arbitrary variable is 0. So what does that mean? This by itself is strong. Right? If you have a variable whose algebra with all variables is 0, then that variable is trivially 0. It doesn't matter. You can actually change the things. I mean, you could have taken these to be Q and so on, but the result will not change. Now, you may try to prove for yourself, and take this as homework and just try I mean, the Dirac bracket satisfies all the properties of the Poisson bracket. That is important. The Poisson bracket, for instance, is antisymmetric under the interchange of the variables. So you can interchange PA and QB. You can take QB with PA, and then you will see that it will turn out just to be the minus of that. And the first term is changing the first term is obvious. That's the property of the Poisson bracket. That's why the changes in the other term are concerned. I would ask you to just do it. Just and you will see that you will get this property. That is this is minus. Okay? Satisfies what is called the chain rule. It does satisfy the chain rule. When you know the chain rule of the Poisson bracket, Poisson bracket, you know, is that if A Poisson bracket is BC, then what is that? That is A with B, C plus E. And this you know, the chain rule. And you can just prove for yourself that this holds. Yes, this is the chain rule. The real difficult proof, the proofs for this are straightforward. There is no big deal in it. The really technically the most complicated and elaborate proof is the proof of the associativity law. The associativity law is what? That's basically the Jacobi identity. The Poisson bracket satisfies a thing which is called what? The Jacobi identity. That is, if you have a double Poisson bracket, that is the Poisson bracket of A, B, C, this is a double Poisson bracket, and if you take what you call CP, that's the mean cyclic permutations, A, B, C, then you should have B, C, A, A, B, two more terms. So all that added together is 0. This will hold for the Dirac. And the proof is difficult, but it will hold. This is like this. And finally, there's another thing. This is called actually the separability theorem. And what is the separability theorem? The separability theorem is as follows. This is used in practical calculations. I mean, if you have a rather big second class system, a big second class system, suppose you have a large number of second class constants. Suppose you have 8 second class constants. Then if you have 8 second class constants, what is the matrix? That is an 8 by 8 matrix. You follow. Each element of that 8 by 8 matrix is the Poisson bracket of those objects amongst themselves. Right? You have 8 constraints. So, say phi 1 to phi 8. Then the entry here will be what? Phi 1, phi 2. Or phi 1, phi 1. Phi 1, phi 2, phi 1, all the way to phi 1, phi 8. Then phi 2, phi 1, phi 2, phi 2. So what is it? 8 by 8 matrix. Then to compute the Dirac bracket, you would invert this 8 by 8 matrix. I mean, this analytically is almost impossible, and even the machine may not be all that helpful always. So there is what's called a very, very important theorem. And what does the theorem say? You have to be clever. You have to be clever in isolating the second class vector such that they are within themselves second class, but across the border they are first class. So like India and Pakistan. So within this, the being second class, within this also second class, but the two, they do not mix. Huh? So the situation is like this. Let me take a simple example. If you have 5 1, 5 2, 5 3, 5 4, okay. Now, if you can find within this 5 1, 5 2, 5 3, 5 4, say 5 1 and 5 3, it is second class within itself, right? 5 2 and 5 4 is also second class within itself. But this sector and this sector, I mean, they are first class. What does that mean? That means that although 5 1 with 5 3 has a second class behavior, but 5 1 with 5 2 may have a first class behavior. Right? So in that case, the whole 4 by 4 matrix can be split into a block diagram or 2 by 2 form. You get the point? Right? So yeah, all these entries are there. But with this identification, with the way that I have told you, if you can isolate that, something like this, right?
But there will be zeros in the middle as well. I mean, it's an anti-symmetric matrix. So
yeah. But this square is there. By that I mean everything is not zero.
Correct.
Here, everything is zero. That is right. Now, then what happens? You can then just consider only this sector and compute the Dirac brackets just with this. So this will be called the intermediate Dirac bracket. Then you go to the next step where you take this. So just as you have used here, on the right hand side, what is there? Everything is Poisson bracket. Okay. So now this is the step 1. I have done it with the 2 by 2. I have got the answer for this. Now when I will go to the step 2, what will happen? This will be step 2 and this will be step 1. You get the point or not? You followed. Huh? This is the way you can compute the Dirac bracket for big matrices by splitting them into block diagonal form. So this step 1 is obtained directly, right hand side Poisson bracket. Now in the next stage, Poisson brackets are all gone. The Poisson brackets will now be replaced by star 1 brackets. The star 2, this is the final sector. This will be defined by taking the Poisson or replacing the Poisson bracket with star 1 brackets. And the answer for star 2 will be the same as if you had done it for the whole 4 by 4 inverse. So this is very nice because say you have 8 by 8, you break it into 2, 2, 2, 2. Because inversion of 2 is trivial, or it is not, may not be trivial, but it is very simple, right? Then you can just go on. So the real intelligence part or the adaptability part is how you have to isolate the constraint. That's the thing. So this is a technical issue of the second class constants and how you can really do. Okay. So this is the method given by Dirac to tackle the second class constraint. So what happens is if you have only second class constraints in the theory, then you can do your quantization by replacing your Poisson brackets by Dirac brackets, and then lifting these Dirac brackets to the level of commutators, and subsequently setting all the second class constraints to be strongly zero. Once you set the second class constraints to be strongly zero, you can actually throw away some of the variables, because these constraints are some relations between the coordinates and the momenta, and since they are strongly zero, you can actually identify the actual canonical of the physical space of this system, of this constraint system, in this way. This is called the reduced space quantization. It is called a reduced space quantization. If you have a mixed system, that is, this is the more complicated one. I mean, you can have second class pure, as I told you. You can have a pure first class. Gauge theories are usually pure first class. Then there is no need to, at this point, to introduce Dirac brackets. You can work through with Poisson brackets. You can define the physical subspace, as I have told. You can go ahead and even, as you know, you have heard of gauge fixing. If you gauge fixing in the conventional language, when translated in the Dirac language, means that you are converting the first class constraints into second class constraints. That is what the gauge fixing does. So you have, for instance, the first class constraint, the Gauss constraints in the macro theory. Then you take the Coulomb gauge, divergence of A is equal to 0. This just converts the first class constraint into second class constraint. That's what you are actually doing. And once you do that, then you have a new system of constraints. What is this new system? You have the constraints which came out from the theory, primary, secondary, whatever it is, but then you have another set of constraints we introduced by hand. These are called the gauge conditions. In Dirac's language, they are called the gauge constraint. And taken everything together, this is now a second class system, and you can proceed in that. For a mixed system also, you can eliminate the second class constraints by the Dirac prescription. You have only the first class constraints, and then you can proceed. All these gauge fixing approaches or second class approaches through the Dirac bracket are reduced space quantization. The other thing is what is called the extended space. Now this is the basic philosophy of what is called the BRS quantization. BRS quantization does introduce more fields. So what is actually the physical meaning of this? The physical meaning is simple. You can actually convert the second class constraint into a first class constraint by introducing more fields into the whole theory. So that is easily understood. I mean, suppose you have a constraint like say this Q1 is equal to 0, and then we have another constraint like this, and you can see for yourself that this is a second class set. It is a second class set because although Q1 with Q1 is 0, P1 with P1 is 0, but Q1 with P1 is not 0, it is 1. Therefore, this is an invertible matrix. You will have zeros on the diagonal, but non-zeros or 1 on the off diagonal, 1 and minus 1, which is an invertible matrix. It is a second class system. Now, it is trivial to convert this into a first class system. So what you have to do, you have to just change it, say like this. So I introduce a new set of variables, new set of canonicals, and you can immediately see that the direct sum, this constant with itself is 0, the bracket is 0. And this is also 0 because with Q1 with P1 you will get 1, but that will be cancelled by the capital Q1 minus P1. Therefore, this is what? This is a first class system. Right? This is the essence of the BRS. This is the essence of the BRS equivalence theorem. You have to introduce more and more fields into the here. So here we have introduced these fields, these variables. These are the new variables such that you enlarge the space, and the second class constraint is now first class one, the whole system is first class. Then you can completely forget about Dirac brackets and so on, and you can proceed with your quantization or the analysis to model just as you do for a first class system.
But with the new variables.
Yes, within this extended space, taking everything. This is of course a more powerful approach. It is a more powerful approach for the following reason. Given the extended system or the enlarged system, there is a gauge, there is a particular choice of the gauge which will take you to this. Now that's a trivial gauge. If I set Q1 equal to 0 and P1 equal to 0 as the gauge conditions, I will go back to the old system. Right? But I can choose any gauge. I could have taken a gauge like Q1 plus P1 is equal to 0. That will give me a totally different thing. That will give. So I have a much richer structure, and that is the reason the BRS technique is so popular. It gives me a much more richer structure. I can play around and see many things which I would not have been able to see otherwise. So this is the basic philosophy of this approach, BRS. Right. The other thing and the last thing which I will discuss. Well, as I have told you, I will finally take the example of the Maxwell theory and work out everything so that you know what is what. This is called the how to find actually the gauge generator. Now, what is the gauge generator? Now, let me take an example. Everybody of you know, or at least you know, must have seen this Lagrangian. This is the famous Maxwell's free theory. You have seen this. What is your name?
Sir, Rabin.
You are what? PDF here? No?
Yes.
You're from Bananas. Yes. Okay, so all of you at some point must have, except you, this Jadavpur? No. Have you seen this? No. I didn't. So he says no. Jadavpur. This is not even seen this afternoon. Then everybody has seen this. Anyway, you should see the Maxwell theory. And this is a course, or this is the Lagrangian which everybody knows. I hope you know that this has, this is a gauge invariance. If you change a mu to something like this, then the theory doesn't change. You know this. And it's not a very big deal to realize this. F mu by definition, the field tensor is d mu a mu minus d mu. Right? So if you make a change by like this, so this is a mu plus d mu alpha minus d mu a mu plus. And then you can see the second term, d mu alpha minus d mu, whatever, you interchange the derivatives. And this term just cancels. And so this f mu itself is preserved. So if f mu itself is preserved, obviously the composite object, the product of f mu with f mu is also preserved. That's it. So this is known as a gauge transformation. The question, what is the generator of this transformation? This is not easy to answer. This is not easy to answer. Everybody knows this. But for it to be a symmetric transformation, there has to be a generator. What is that generator? This is not an easy question. We will try to provide an answer to this question. And what do we mean by the generator? You know what we mean by the generator. So, suppose this is the generator G, then this is the infinitesimal transformation. This is what? Delta mu z degree of alpha. So, delta of A mu should be something like this. Isn't it? That is what we mean by generator. We have to take the algebra of G. That's what we do. You suppose, if you take the translation operator, due to you get the partial in x. Take the rotation operator, you will get the epsilon I or whatever it is. That's how you get. So what is this G? What is this G? Such that horizontal bracketing with this will give me this. It's not an easy thing. Yeah? It is not an easy thing. To answer this question, you have to actually realize a very fundamental thing. What is the fundamental thing? I go back here. Suppose you take an action like this, L. Now, I hope you know that for the stationary variation, this is what will give me the Euler-Lagrange equations of motion. This you know. Take this to be a function of, say, the simplest case, the cubes of the dots, and then you can take the variation. So let us do this. So you get something like this, isn't it? Then know this, yes? And then if you ignore this total time derivative, because if you consider, say, the fixed points, so that delta q vanishes at those things, and then you say that if you want this to be 0 for arbitrary variations of delta qi, then you get what's called the Euler-Lagrange equations, del qi minus ddt del qi delta. That's it. Now what? There is a point which goes unnoticed. There is a point which goes unnoticed in this derivation. This is the following. You actually commuted the time differentiation with the variation. Right? And actually, the demonstration which I will give here is one of my earliest works in constraint dynamics, where actually I was the first person to show that if you translate this in the Hamiltonian language, you will immediately get the generator of the G transformation. Okay, that's the whole point. That was my observation, that at the Lagrangian level, you have actually commuted the time differentiation with the variation. Right? You have pulled this through. You have taken delta ddt equal to ddt and pull out through. Okay? That's what you have done. You get the point. Then you have ddt, but you take the ddt out. Hello? Class আছে class. I hope you have followed this. This is a very subtle point in the Lagrangian prescription, and it gives rise to very non-trivial consequence when you translate this in the Hamiltonian framework. Why? The reason is as follows. If you take ddt of an arbitrary variable, exactly this, right? This is this. Okay? So, this is this. This is this. You read. This is this one. What is this? This is this. Okay? And in the next lecture I will show that if you equate the two, and I'll find a definition for G. Okay? And G will actually be defined everything in terms of the constraints of the system.
Here you have written delta A mu equal to G A mu. So there you have delta B equal to Q G.
I don't care, it's just not your sign. Right, yeah. I mean, it's not that important whether you take some definition. Okay, so I'll discuss this in the next class, and which will be the last one. And I will back this general discussion with a complete analysis of the issue, and actually explicitly derive this. And this has nothing to do with, it is a very general prescription. You can do this in any, I mean, complicated theory, non-resonant theory, gravity, string theory, anything. Okay, that's all. But make sure, Fernandez, this is not, you have to fix the room correctly. This jumping like a monkey from this floor to that floor and then going from here to there as well.
So I think next time we'll have it on this in this room itself, and I'll talk to them about how it's vacant.
Talk to them and fix it 72 hours before. It's like an operation theater, you know that. Everybody wants to be
Right.
here. So next week I will tell on perhaps on Monday when I will vote this one.